one of the key reasons that dynamic geometry gained such good penetration in schools was the argument based on the idea that objectifying mathematical concepts made them available for analysis both by researchers and teachers. And so you could actually understand something about the student's reasoning by having it in this dynamic geometry form, which was more descriptive than what you could have on paper because you could see some of the process and all that. And that's true for individual work. And I have to say that I've studied a fair number of classrooms where dynamic geometry is in use, and the funny thing is that even the single-use tools, you don't actually see that much single use. You know, even when the teachers assign individual assignments, you see a huge amount of collaboration taking place, not by design, but by happenstance. And so I'm sort of wondering, the thing here is that it's a virtual collaboration and that we can log that as well. But I'm wondering how much of this is really piggybacking on what's already there in dynamic geometry environments like Cabri and Sketchpad and GeoGebra, and what is it that the virtual component brings that isn't there in a face-to-face classroom where they're grouped around a single tablet or a single machine or something like that?
Well, I think it brings different things for different people. So for students, one of the things we found is important is persistence. So the fact that they can always go back to the chat room and all of their chat is there. They can scroll back through the chat. They can scroll back through the history of their construction. That turns out to be quite important. So textual chat is, has that advantage. Just the chat, the fact that they have text chat rather than speaking has the advantage of persistence. So they can look back and they can point back to a previous chat posting and they can respond to that later on. Whereas when you're speaking, it's hard to say, well, I like the point that you made 3 minutes ago, which was blah, 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 if I got it right, and I don't really remember it. But usually when you're speaking, if something is more than a couple utterances back, you just forget. You know, you missed your opportunity to respond to it. Too bad. Well, just move on. But with the text chat, you can always go back to that. And in a complicated mathematical construction, you may go down some, garden path, detour, and then want to go back and say, oh, so-and-so had this good idea back there that we ignored, but now let's go back and try that. So persistence is important for the students. For the teachers, if you have groups around the classrooms, even if they're in a classroom where the teacher's present, the teacher can't be listening to all the groups. But here the teacher can go back and review what each group did in as much detail as they want. For the researchers, so my concern is that we capture the whole group interaction. That's very difficult in face-to-face. If you have, say, 3 students or 4 students or 5 students working together face-to-face, you probably need a camera on each of their faces, a camera on the screen, a really good microphone, or maybe 3 directional microphones or something, and then you have to coordinate all of that. When you're reviewing it, it becomes an impossible task, and then you can't hear some of it, and you have to put a little question mark in the log, and you have to transcribe everything from audio, and how do you do? There are problems with that. There are problems with the video angles and the lighting, and all of that. Forget all of those problems. You've got an automatic transcript that's complete. It looks exactly like it looked for the other students. Any typos, whatever, it's all there. All the actions are there in as much detail as you want. And it's all automatically there for all of the sessions. And so for a researcher, it's just great. And if you want to understand collaboration, you really need a complete record. You can't say, well, they might have been talking about it when they went outside the classroom, And they might have been whispering things or writing something on a piece of paper and showing it to each other that you didn't capture in the video. That just ruins your data. You can't make an argument if you don't have a complete record. And so this gives you a complete record. So for the researcher, I think it's really important. People always ask, you know, why don't you give a speaking channel to the students so they can talk instead of having to type everything? Well, that would be nice for the students, but for the researchers, then you have all these audio files, and then you have to either transcribe them or keep clicking on them and listening through the whole real-time sequence. And so I have to admit that the system is in some ways designed to optimize research. And in the future, we might go to an iPad with the voice channel, and it won't be as good for research, but it might be, you know, more fun for the students.
Sort of answers my question about the difference between design-based research and design in this case. I think that's very interesting.
I had a follow-up on that too, because it's different if you look at it from a classroom point of view, where the students sit in a classroom. It would be quite unnatural for them just to chat, if they would want to chat with each other.
Right.
And as research concerning, they would probably talk as well then, and you would miss something anyway.
Right.
Could you elaborate on, have you thought about implementing this in
Yes, my preference would be to have students work together who are at different schools.
Yes, as we talked about.
So they have to rely on the internet connection.
Yeah, so they would not be able to.
When I've done it
in the class.
when I've done it in my own classrooms, I have students in each group sit apart from each other, so they can't really talk to each other.
They have to design the classroom.
Yeah. But I mean, to say that I would design it differently if it were in a research project, how do you know your design is good if you don't research it? That's the whole point of design-based research, is the iterative process. We try it, we see how it works, and then we change things constantly, you know. And we're just changing. I can't even say how many iterations we've been through, because it's really a constant process. We have a full-time programmer, and after each time I look at some student records, I go to the programmer and I say, I want this new feature, or I want you to change how that works. And if you say, oh, let's forget about research and let's just design it for the students, how do you do that design? How do you know it's a good design if you're not researching it? You know, how do you go to the US government, which is big on funding education, and say, we want to fund this, and they say, well, where's your research showing that this is a good way to teach geometry? If we haven't done the research, then we don't get the funding to do that. They want research-based designs. So it's not that simple a contrast between the two ways of designing.
Thank you for a very inspiring talk and these rich tools that they are using. And I'm thinking about the interaction with the tools and my dependency on tools in terms of the specialized vocabulary that you started with. Have you seen any developments in terms of how they develop this specialized vocabulary or not? Or does the tool trigger that too?
Well, the vocabulary is largely the vocabulary of geometry. So they learn, you know, what equilateral means versus isosceles and right angle and congruence and similarity and things like that, just like they would in any geometry class. Some of it is used in the curriculum. So and the curriculum all consists of these little text boxes that say, here's a picture of several triangles, which one, has the dependencies of an equilateral triangle, which one has an isosceles, and it might define it the first time that's used. Or it might say there are lots of triangles. An equilateral one has all three sides the same. An isosceles has two sides the same. Another scalene has 0 sides the same. So it might introduce vocabulary that way. And then the students pick it up right away and start reusing the terms. The term that I've tried to focus on is terms related to dependency, because I really want them to get that idea. So terms like restricted, dependent, constrained, and they start to use those, and they start, one student asks in this data, what does constrained mean? Or what's the difference between constrained and dependent? And the others try to answer that and point to examples. And little by little, from session to session, you see them becoming more confident at using those terms and relating them to the problems that they've worked on.
Because that's important. I mean, a lot of screen work otherwise becomes very didactic. The kind of language is people, they point to things
Right.
and drag things. But that's a good thing if you can see that.
Picking up on what Osa said, I did a study of TI-inspire use, actually the design and use of TI-inspire. And one of the things that I saw in that was, especially studying the development of it, they went through a number of iterations where there were conflicts in the language used in the software. There were conflicts to the language commonly used by teachers and also commonly used in different curriculums in different states. And the schools I were in Ontario in Canada, so in the Ontario provincial curriculum, I noticed in the schools there was quite a conflict between the kind of terminology used in the curriculum that the teachers were expected to cover with the students and the terms used in the menus, as basic as in the menus in the software. And what I found was that the students were using the terms in the software, not the terms in the curriculum or even the textbooks, because those were the terms they were operating with all the time. And many of the students developed understandings of terms that were well beyond the grade level that they were at, because they were accessible as features in the software. And I'm wondering, how much have you had to work with sort of aligning the language used actually in the tool for describing different features to the different curriculums and different mathematical sort of languages?
Well, GeoGebra basically uses the common language of geometry.
For instance, I was interested with the set you say proof, because there's sort of if you look at the recent NCTM conferences, for instance, there's been sort of a conflict going on between people that don't think that the inductive proof that students can generate in dynamic geometry is enough to qualify as mathematical proof. They want to see a deductive. They want to see a more traditional deductive proof. So like just that word proof is conceptually quite different depending on who's using it.
Yeah, proof is a very controversial term in geometry education. And that's why I am interested in emphasizing dependency, thinking about dependencies. Because I think dependencies in a geometric figure, the dependencies are the basis for deductive proof. So what Tom's referring to in the literature on dynamic geometry is that at a certain point in the research literature, some people made the argument that dynamic geometry has a negative consequence for teaching students the importance of proof. Where proof is traditionally you put down, A is equal to B, and then the reason is because of theorem number 17, and then the next step is this, and the reason is this theorem, and so on. That kind of deductive logical proof. And first of all, geometry education more and more got away from teaching that in the last 50 years. But then people made the argument that if students use dynamic geometry and they see by dragging something, they create an equilateral triangle and then drag it all around and see it always remains equilateral. They say, well, now we've proven that this triangle is equilateral because we can't drag it any way that makes it not anymore look equilateral. And so they feel, the mathematicians feel, well, the students now have no reason to do an axiomatic proof because they've convinced themselves that in fact this is true, that this triangle is equilateral because there's no way to make it look like it's not equilateral. So I don't have to prove that it's because the sides are equal to radii of circles that have the same radius and so on. And so that's one reason that I don't like the way that GeoGebra and other dynamic geometry is often used in classrooms, where the whole thing is just having students drag things around. But I want to have them start thinking about constructing the dependencies. And then they see, like we saw even in one of the slides here, they're talking about equal radii. And that dependency that things are based on equal radii, that's the whole basis for then going on to make a formal proof. Now, the students we had here were, I think, 14 years old. So nobody would be teaching them an axiomatic deductive proof. But here we can see that they're getting the core concepts that underlie if they were to go and make a deductive proof. They've basically got it. They may not be able to articulate it up to the standards of, college math deductive proofs, but they've got the basic concepts there. Whereas if all they're doing is dragging, then it's all a matter of how the geometry looks. So in the research, there's a famous theory called von Healy levels, and it's sort of like levels of like cognitive levels. So young kids judge things by how they appear. Oh, that looks like a triangle, or that looks like an equilateral triangle. Just from like baby toys already have things that look like circles, things that look like squares, things that look like triangles. So from that age on to middle school, they judge geometry by how things look visually. And then a further level is, there's several levels, and the final highest level is that of a mathematician with this deductive axiomatic reasoning. So we have this axiom that says this, and then that implies this, and that implies this based on this axiom, and so on. And therefore, we get the result. We've proven the result axiomatically, formally logical. And there's a number of levels in between. And so our curriculum is sort of designed to move students from one level to another. And for a middle school curriculum, we never get to the point of a full axiomatic, rigorous proof, but we do try to get this idea of the dependencies and how to design the dependencies in that starts them to think about things in the terms that are used for proofs. And I even, I guess in tomorrow's lecture, are you going to be there tomorrow? Yeah, that's too bad, because I show how even some of the advanced theorems, like Euler's segment and the 9-point circle and so on, can be proven based on the dependencies that are designed into the construction. And so even for something that goes beyond Euclid's proofs into fairly modern math proofs, it's based on the dependencies that are designed into the construction. When I discovered this important role of dependencies in my research, I was shocked when I went to the research literature and I couldn't find anybody talking about it. about the relation of dependencies to proof in geometry. And because to me it's just core to dynamic geometry. In fact, the dynamic geometry software is designed based on dependencies. They have something that they call dependent objects. They differentiate in the highest level of the software description about dependencies, but nobody in the research about geometry education had hit on the importance of that, which I found shocking. I finally found somebody who had a little quote about it, but and it's really ignored in the educational use of dynamic geometry. Most places, more and more, they're getting away from that kind of focus into a rather superficial use of the software, which I think is a shame. But I mean, you know, teachers, with all the pressures on them, they just feel that's the easiest way to use the tool, and then they end up not using it. So the school systems pay a lot of money for Geometry Sketchpad, and they use it less and less, and then not at all. And it's just a waste of the potential that's there. And I think if they started to, obviously, if they started using my curriculum, they'd be on a much better track. Now, if they started using the more fundamental opportunities that dynamic geometry provides, then they'd get a lot more out of it, or their students would get a lot more out of it.
I was thinking you started up your lecture by saying that technology changes so fast, and even if this is a design-based research and very particular results come out of that, do you think it's possible to say something general that could help us through new technology inventions in relation to learning and collaboration?
Well, I think we want to design software that supports collaboration, and I think that's the big potential of computers in the first place, of network computers, of the web. The big potential of the internet is to network people together so they can work together, they can learn together. And it just hasn't happened yet in a real way. I mean, the state of collaboration technology is just pitiful compared to what it should be. It's because commercial software is guided by corporate interests, and the corporate interests aren't in collaborative learning. They're interested in business communication and things like that. And while they put in icons that say, you know, like me and go to Twitter and all of this, it's not really providing core support for real collaboration.
Are you sure?
Yeah.
You are?
Yeah. And I did read your article, you know.
I'm not quite sure of that, though. No.
It's not what I think the potential is.
We actually have a PhD students here studying likes, so yeah, and what they mean in different contexts.
And then the other thing, I think dynamic geometry, like I've said, has a potential there to teach students to view the world as a design project. The world is there to be created by us collaboratively. And if we view the world as, you know, something that's there that can't be changed, and we just have to, you know, learn to live with it and view it superficially, then you know, that's not my goal. So my goal is for the students to say, we've constructed this ourselves. We understand this because we've constructed it ourselves. We put in the dependencies that we want to have in it because that's what we agreed on as a group. This is our geometry. And we can even go on and create our own tools, custom tools, which I don't think almost anybody is doing in the classroom these days. you know, they reduce it to pretty pictures that the teacher downloads some geometric construction from the web that some other teacher has developed. They put it up there. They might drag it around on their smartboard in front of the classroom, and that's it. The students don't get even to drag it around most of the time, probably. Or if they do drag it around, they only change the visual appearance. They haven't created it themselves. And so I think it's really important, and it's a hard sell to teachers or to anybody to really teach students the construction. It takes time and experience to learn how to use these tools to construct your own objects, and to think about them as designed objects that our group has designed the way we want it to work. And we understand the principles of the dependencies that we've built into the geometric design. And so I want to develop the software and the curriculum and the whole package that promotes that way of looking at it.
Send it over to Sweden as well.
What?
And you can send it over to Sweden.
It's there. You can use it. It's right there on the web for free.
Perfect.
Yeah, just to follow up, this is very interesting. I just sort of came to think whether there is something quite specific to this example or this way of using the technology, which gives particular premises for collaboration. I'm thinking about, we had an interesting discussion over lunch about a paper from Sweller, Kirshner and Clark, where they really argue against minimally guided approaches to teaching, as they describe it. And I think this is a really, in a way, an interesting example of a minimally guided situation, which still is really productive, as you demonstrated here. And I'm thinking, is there something in that you have a tool which it doesn't guide the sort of collaboration, but it gives a clearly defined problem space. It also gives certain dimensions of variation, if you want to call it like that, which you can sort of experiment with. And you also have to sort of, given that it's a group situation, you also have to explain you have to give your arguments for why you want to solve the task in a particular way. And also you have this, as we all already been into, a mathematical language. So you have many factors here which really sort of constrains also, in many ways, the possibilities. And I think that's what I'm thinking about here. Is there a sort of, could the effects, the really good examples you have here, be due to this balance between constraints and openness in the situation?
Yes. We have played quite a bit with this spectrum between guidance and open-endedness. And we keep revising the curriculum, especially along that spectrum. And so you have to teach, in a sense, you have to teach new students a lot. So if students haven't worked together in a collaborative learning situation, they have to learn how to get in the software and how to communicate in it in an effective way, and how to problem solve collaboratively. And then in addition, they have to learn how to use all the tools of GeoGebra, especially if you want them to do their own constructions and you even want them to make their own custom tools. So there's a lot for them to learn. And it takes time for anybody to learn it. And on the other hand, you want them to end up being able to do things that are very open-ended. So this constructivist idea of creating a micro world in which they exist, a math world, say, a geometry world, the world of geometry. You enter it, and then you can go wherever you want in that world and choose your own path and your own destination and so on, collaboratively. And so the more advanced curriculum is like that. We say, suppose you had, you were designing a factory and you had objects on the assembly line that were shaped like polygons, so they're geometric figures, and you want to move them around. What's the easiest way to move them around? Translation, rotation, flipping, and so on. And how do you combine these different transformations? And if you had machines to do each kind, how many machines would you need? And what would be the most effective or minimal set of tools that you would need? So really exploring transformational grammar, to use the mathematical term, in a concrete situation. And just give them that problem and let them figure out where they want to go with it. And that's one of our curriculum units. But that's after they know how to use GeoGebra, how to collaborate together, how to discuss things, and so on. So we build towards that. And we have the course for teachers. So most of the teachers there have not only taken geometry, but they've taught it maybe for a few years. So they know a lot about geometry already. And they have their own ideas about what geometry is all about. Whereas if you take 14-year-old students who haven't taken a geometry course yet, there's quite a difference. They're actually much better at a lot of things. So, including exploration, open-ended exploration. So, with the teachers, we have to make a much more strictly guided curriculum that'll get them away from their old way of thinking. I'm just kidding. We don't have to step them through the geometry as much. And so we have them explore and discuss, reflect upon what they notice about the geometry, even in the early lessons. Whereas the students we guide more, probably, through the early steps, to get them to focus on talking about the things we want them to talk about, like constraints and dependencies and design issues. So the spectrum from guidance to open-ended is basic to what we're experimenting with in the curriculum design. And I don't know what paper you read, what their argument is against minimal guidance or what they mean by that. But
there's a whole discussion relating to cognitive perspectives, and I just sort of thought that this example is quite interesting in relation to that discussion.
Yeah.
Actually.
And I might disagree with them, I suspect. Yeah, that's the nature of research. Is just because somebody said it in some paper doesn't mean that I accept it.
You know, on this scale that Patrick was talking about from openness to closeness, you know, one of the things with TI and Inspire was that they got it totally wrong in the beginning. Like, it was a commercial flop because it was way too open. But it wasn't too open for the students. It was too open for the teachers.
Mm-hmm.
And that's what they found, that it wasn't scalable. It worked with their small groups of elite, interested, engaged teachers that would come in and do their workshops with them. But it didn't work at scale with teachers out in the field. And what they had to do was do subsequent versions of the software which brought in more and more constrained kind of scripted teaching, resulting in these algebra-inspired packages and stuff, which are just like, I mean, you can basically roll it out. You don't even need a teacher. You just need a human. Like, you don't need any like teaching skills whatsoever to roll out this package. And it sort of makes me wonder, you know, in this, you haven't talked that much about the teachers. I mean, how does, because one of the problems, you know, the TI had was that when you give the kids a super open tool to work with, or a super open curriculum, they go off in all kinds of mad places, which are super interesting for them, but it's incredibly stressful for a teacher that has very limited mathematical knowledge. And especially at the middle school level, the teachers are often pretty basic in their mathematical knowledge, and if the students start to go places, it's a risk for them. And so I'm sort of wondering, where's that? Is this an issue for you in terms of scalability of this software and this curriculum? Like how's it going to work with these teachers that are maybe not even teaching in their subject area?
You mean how's it going to work for the students of teachers?
Yeah, I guess that's the. But if you have to, that's the thing about education technology, right? You have to convince the teachers first.
Well, you have to convince the principal first.
Yeah,
And the school district, you know, to buy the software or to use the software in this school. I mean, that's the problem with educational software in the first place, is that the decisions are usually made by the superintendent of schools, not by the students. And there's a big difference in their priorities. So I think of the curriculum in terms of resources, the concept of resources. So I look at the curriculum that we've developed as a series of resources that are used sequentially by the students. And resources are in the research literature, there's a lot of discussion about, they use other terms other than the word resources, but for what I call resources, whether you call them artifacts or problems or topics, a lot of recent research about how they evolve. So the first thing is the students see something up on the screen, which I think, since I wrote it, I think it's as clear as possible. This is what I want you to do, step 1, step 2, step 3. What could be hard to understand about that? So the first thing that the group of students does is they have to understand what's there. First, they have to orient to what's there. They come into the chat room, they probably don't even look at that text. They start fooling around with whatever they think looks like fun to fool around with. Eventually, they realize that they're supposed to be focusing on what the text says, starting with point number 1. And then they glance at point number 1 and they say, okay, we've done that. Now, shall we move on to point number 2? So they start chatting and communicating and negotiating. What is it we're going to do here in this room? And they start interpreting what's in that text box as a resource that we put there for them. And over time, they learn that when we come into the chat room, we're supposed to look at the text, we're supposed to carefully read and think about step 1 of the text. That may take a couple weeks for them to get to that point. And they get to that point because they've gotten off track and screwed up and haven't accomplished much because they haven't carefully read and thought about what that means. So thinking about what that means, they have to interpret what that means. They interpret what that means in their own terms. They discuss it in the language that kids use to talk to each other. And they come up with something, let's try this. And so they start doing something in that chat room, either typing chat or moving GeoGebra objects around or whatever. So, and then they decide, this is what we're going to do today. We have an hour. This is what we're going to, basically, in essence, what they say is, we have an hour. This is what we're going to do as a group. They won't put it in those words, but you know, we're going to try to get through these things. And so through that, they define their problem. Basically, they're saying, this is our problem as a group. Today, we're going to do X. So this problem statement, while I might have thought, as the person who designed it and wrote it, I might have thought it was perfectly clear. It's not perfectly clear to the students. They have to interpret it. So that's one stage. And then they have to interpret the tools that they're using for GeoGebra. How are we going to use these, and which tools should we use, and all of that. And then they have to go through a process of exploring, like dragging the points of the triangle around, seeing what happens. If I drag point A, what happens to point B? What happens to this? What happens to point D? Oh, I see some of them follow each other. oh, look, some of them are colored differently even. I wonder if that has some significance. So then they start to interpret what's going on there. And based on that, then they do their next steps. So the resources, even if it seems like it's pretty specific, it ends up being quite open-ended in terms of how the students interpret it. And then when as a researcher, I go back and I look at their chat and I see how they've interpreted my words, and then I go back and I modify that resource to be more effective in the way I wanted it to be. So it's quite a complicated process. And the role of the teachers, I mean, so last year we trained a bunch of teachers with some of the GeoGebra problems, GeoGebra resources, and then asked them to make their own curriculum for their own students. Well, that was just impossible. It's such a complicated process to design a coherent curriculum, to introduce students to something as complicated as this whole software package, including GeoGebra, including understanding the elements of geometry, if they haven't had that. It's just so multi-layered that you can't expect somebody who's just spent a couple weeks and done a couple exercises themselves to come up with a coherent curriculum. Most teachers aren't trained in curriculum development in the first place. They use a textbook. They, today we're on this page. Tonight I better read this page because that's what I'm teaching tomorrow. And they don't develop their own approach to geometry. They follow a textbook that they've been assigned to follow. And to say, not only you have to develop a whole curriculum yourself, like writing your own textbook, but you have to put it in a format that works in this online environment that's oriented towards collaborative learning. And you have to have prompts in there to prompt the right kinds of discussions that you want to get out of it. It's taken me years to develop those resources within a group of people, which includes other people in my research group. We've had anthropologists, conversation analysts, a lot of math educators who do a lot of training of teachers, math teachers and so on, all working together to come up with this over a period of years. You can't expect a teacher in a couple hours, with all other things they have to do to develop it themselves. So they help guide the students into groups and encourage them to do it and talk about it afterwards and things like that. But it's a fairly limited role for the teachers, the way we've set it up. Now they can, if a teacher wants to, they can try developing their own resources. But I wouldn't expect most teachers to do it for the whole sequence. And there's these issues like the spectrum from minimal guidance to open-ended. It's a really subtle thing, and you can't just do it. You can't say, well, I believe in minimal guidance, so this is the way I'm going to do it. You have to try it out over and over again and keep revising it and seeing how those revisions work. Nobody can create an effective curriculum like that without repeated revisions and trials. And then in each situation it's different. It's different for the groups of teachers than it is for the groups of their students. And it's different if you have honors students, and it's different if the students are already in a geometry class, or if they know each other, and so on. So, teachers are really good about understanding their own students. So you need to work with the teachers to tune the curriculum to their students, but not to expect them to do the whole thing on their own. Because if you do, then they just reduce it to the minimal thing, which is just let's show it on the smartboard in front of the class and not have the students touch anything.
I have an epistemological question.
Good.
In mathematics.
Uh-huh.
To finish the talk with. Yeah. How do you view the fact that all dynamic geometry environment are based on analytical methods instead of geometry, actually. It means that you can do a lot of more than just Euclid geometry, for instance. I mean, Euclid proved, and so did Gauss, that you can't construct a regular 7-vertex polygon, for instance. But you can do that in GeoGebra and in Gerry and in geometric sketchpad, since they are based on analytical methods instead of geometry. So you create something to show Euclidean geometry by using methods beyond Euclidean.
Yeah, so what I do is I limit the tools. I limit the tools to only those that are equivalent to straight edge and compass.
Okay, so you take off some of the
So I start them out by saying,
instruments.
construct a point. Euclid knew how to construct a point. Construct a line or line segment. And eventually construct an equilateral triangle using Euclid's method, using only a compass and basically a straight edge to connect 2 points with a straight line. I limit the tools that are available in GeoGebra to those, and the guidance steps them through that. And it steps them through constructing the elements of Euclidean geometry without the Cartesian coordinates and so on. And then for the more advanced things, we let them use the full range of tools. But only when they understand the dependencies that are built into those tools.
So you guide learning
Yes.
by taking off some parts of the tool. Right. So I'm not sure that that's the way to do it, but I think that teachers, especially mathematics teachers, should be aware of that it's not an Euclidean geometry that's beyond GeoGebra or any dynamic geometry. It's analytical methods developed 2000 after Euclid did it. So that's why we had them today. We didn't have the instruments at that time, so to speak. But teachers should be aware of that we could do a lot of stuff that Euclid couldn't do.
Right.
Yeah.
So that's part of the long-range potential of the software, is that if they learn the basic use of it, not just how to do things with the tools, but conceptually how to use it in geometry, then they can go on and continue to use it as a tool for thinking mathematically for more advanced forms of mathematics, certainly for analytic geometry and trigonometry and calculus and so on.
One point more. There are actually some studies, not so well spread, but it seems that students are given the opportunity to prove by doing investigations by dynamic geometry. So Colette Laborde has written some about that. So it could be the other way around, that actually proofs are coming back by doing investigations or conjectures and so on by dynamic geometry. So I'm not so convinced that proofs will vanish or go away. I think
No, neither am I. When I responded to Tom about this discussion in the research literature about dynamic geometry, saying that there was this argument that it reduces the capability of students to think about deductive proofs. That was an argument that was made maybe 20 years ago, 10 or 20 years ago, and it's sort of, some people remember it still, like here we have an example of somebody who remembers it still, but I think in the literature, then other people like Laborde argued against it, I think successfully, that as long as you bring the students along to these higher levels of thinking, that it can be helpful. And like I said, that's why my emphasis is not on dragging us as the final stage in mastering GeoGebra, but in construction and understanding construction as the design of dependencies. because that does lead to proof. And supports thinking in the ways that mathematicians have to think about in order to create proofs. Yeah, so I think that the old-fashioned two-column proofs have kind of disappeared, but there still should be an emphasis on understanding and being able to explain, even at every level, even for someone who's not doing a full explicit deductive proof. Every student should be able to explain why something works, why they think something works, which is a stage, a higher stage than saying it just looks right, but giving some reasoning why it's constrained the way it is, which is another one of these levels that leads up to a fuller sense of proof.
I think that would be your last word before the rest of the day. Thank you so much, Gerry.
You're welcome.
You see, your talk was so interesting. It triggered a lot of questions, and we can actually continue our discussion because we're having coffee now.
Great.
In the coffee room downstairs on floor 2, and then we will be back here at 3:30 for 2 presentations. One from Marissa and one from Veronica. Okay, thank you so much, Gerry.
You're welcome.